All right.
Let's get this rolling.
Today and Friday are going to be wrapping up Chapter 7 on dimensional analysis.
Today's a
little bit more
applied.
Right? We've established at this point how we can use this tool of dimensional analysis to take some relationship between a bunch of dimensional variables. Okay. And we can apply the repeating variables to boil it down to a smaller set of dimensionless variables.
So we've
posited that this makes experiments easier because it reduces the number of variables that we have to explore for doing experiments.
So we
haven't really established
what we
do if we were to run experiments. After going through this process of dimensional analysis. So that's going to be today's topic. We'll be covering how we would represent or describe empirical relationships in cases where we're 1, 2, or 3 pi terms in our new dimensionless function. And then we'll apply dimensional analysis very informally to Navier-Stokes see that there are some very common dimensionless groups that fall out of that. That we see throughout physics and fluids. The way in which we describe this relationship, we've established that we're looking for something to the form pi 1
is equal to some function of pi 2, pi 3,
etc.
Where each of these pi terms is dimensionless, and phi is some unknown function. We can't write it out. We need to explore it experimentally and have some sort of empirical description of that. So the way in which we deduce that empirical relationship depends on how many pi terms we actually have. So the first case is for one pi term, right? This is if you value of k minus r is equal to 1. And in this case, we end up with pi 1 equal to basically a function of nothing, which means it has to be equal to a constant. Okay. So this becomes useful in actually quite a few cases. For example, if we start out with four variables, okay, in a dimensional relationship, and there are three unique dimensions contained by those four variables, then our value of k minus r is going to end up being 1. What that allows us to do then is simply perform one experiment, calculate the value of pi 1 that we get, and then have a universal law. So the easiest and most approachable example here is if we consider the classification of a body falling through a vacuum. So suppose we've got some solid object that's got a volume v, a density rho. It's got some characteristics with L, with W. There's gravity up and down. And we're interested in figuring out, if we're assuming we're pre-Newton here, and calculus hasn't yet been invented. Can we figure out the distance why this thing falls in a given amount of time? So by the dimensional analysis, we begin by asking ourselves, okay, what do we think that y is a function of? What variables come into this? Okay. It turns out in this case, right? It's only going to be G and T. The reasons for this are that we've stated this is falling in a vacuum. Okay, we might be inclined to include the density of the object, its mass, something about its size, but the fact is that in the absence of air drag, right, a feather falls just as fast as a bowling ball. Okay. We've seen this. So we are using some physical intuition to say, all right, we're not worrying about air drag. Then really only going to be a function of gravitational acceleration and the time fall. Yeah. If you didn't know that, then you would go ahead and include those items, and they would end up essentially falling out. You could. I'll come back. And I'll visit that at the end of this little example. So stepping through the process we set out last time, right? We've got our step one, which is list all the variables of interest. We've got that right here, right?
Y is equal to
function of g t. Step one. Step two is to write out all the dimensions of these particular units.
So y
has dimensions.
Length.
T obviously has dimensions of time and g is length times negative 2.
Right.
So step 3 is
figure out what our values of k and r.
Right. So
we've got
number of dimensional variables 1, 2, 3. How many reference dimensions do we have? Only two. Mass never shows up.
Temperature never shows up. We have length and we have time.
I'm gonna insert space here.
Step 3.
K minus 3 equal to. Oh, sorry. K minus R. 3 minus 2. 1. Okay, so we're looking for one pi term. Step 4 is select our repeating variables. In this case,
we'll go ahead and pick
G and T. So our repeating variables. Remember, we need R. So we need the same number of repeating variables. There are reference dimensions, and they need to be dimensionally independent from one another. We pick T and G. We've got time here. We've got length, some product, length here. There's no combination of these that allow cancel out both sets of dimensions. We can't form a dimensionless group out of those two variables. So we're A-okay. So G and T as our repeating variables.
Now my choice to conserve space is getting weird here. Step 5
is to form our dimensionless group, right?
Form our pi terms.
So we're saying
pi 1 is going to be equal to y times g to the a power times
t
to the b power,
which leads to dimensions
of length times a length
b
to the negative 2 b.
And we want to set this equal to length 0 time to the 0. So that gives us a system of two equations, two unknowns. Right, for length,
we have
1 plus a is equal to 0.
For time, we've got 2 plus
b
is equal to 0. 1 plus a plus b. That's. I have that backwards, don't I? I'm gonna flip these. B and A.
Go, and that's
time.
Man, I messed this
up.
Let
me make sure I've got this right now. 1 second. Length.
Nope.
Length. I just want 1 plus b.
And time.
I want a minus 2b. Right now. Okay. Set now.
And so what we should get
out of this then is that b is equal to -1.
And if we plug that value
-1 in here,
ends up being 2. Negative 2. Which means that pi 1 is equal to y over g t squared. Okay. So our and then step 6 is verify that it's actually is to repeat this for any remaining variables. We don't have any more variables. Step 7 is to make sure that they're dimensionless. We're going to go ahead and we've got length on top, length per time squared on the bottom, times squared, so we have length over length. All the dimensions cancel out. And then step 8 is to write out our relationship explicitly and sort of think about what it means. So we've skipped over steps 6, 7. Step 8 now is to say pi 1 equal to y over t squared is equal to constant. All right. So the point is how would we use this? How would this actually help us? If we were to go out and take an object, put it in a vacuum chamber, drop it, measure how far it fell, time how long it took to fall that distance. Okay. And if we know gravitational acceleration, this is a key here. We know what value of g is, and we can form right this y over gt squared. We can calculate that. And what we find is that value of c is always going to be equal to 1/2. Which means that we can come up with this expression of y equals 1/2 gt squared using only one experiment. Right. So this is the same relationship. This is the same relationship, right? That Isaac Newton came up with, but without the necessity of calculus. It's an empirical derivation of kinematics. But it requires only one single experiment to deduce. To answer Dylan's question about what if you don't know what terms are unimportant. Okay. And basically, you could blindly go at this, and you'd end up with something that's like pi 1. You might end up with y over gt squared to an unknown function of now maybe you have the length over the width, the density. Let's see. Say you have you'd end up with maybe the density of the object over the density of the fluid that it's sitting in, et cetera. You'd have extra terms, and so you'd need to perform extra experiments. But what you find is that if it's in a vacuum chamber, that none of these terms actually have any effect on your answer. So you're still just going to get 1/2 every time. And so that informs you that those pi terms that I came up with are unnecessary. They don't actually affect the problem. So it requires a little bit of foresight and intuition to make sure you don't go through extra steps. But if you do end up with extra pi terms that aren't necessary, it just leads to some extra work. It doesn't invalidate your answer in any way. So if you don't know what g is, you would need to say, okay, I'm going to assume at least that maybe you don't know the value of g. Okay, but if you can assume that there's an acceleration that's due to gravity, and you don't know that's 9.81 meters per second squared, you could say then that you still can get this relationship, right? You just can't calculate y over gt squared from one experiment. What you can do is you could say that y over t squared is equal to g times c. Okay? You can measure that.
You could measure that quantity.
And now you have
a value of G times C.
And if you
And
also
if you
have
also
it
have
in
it
hand,
in
if you also
hand,
have
if you also have calculus, where you can
calculate
that.
You don't need to know the
You don't
value
need to know the value of
G
G either. You can
y
come
equals
up with
1
y
half
equals 1 half
GT squared. Just for the placeholder.
Just for the placeholder.
This works on
Right,
Mars.
this works on Mars. It works on the moon.
Wherever you are, as long as you have constant gravitational acceleration. You can use your one experiment, and you can use the kinematic calculus. And you can say, well, if I divide t squared by t squared over here with 1 half g, so c must be 1 when you have a measurement of gravitational acceleration. All right. So that's for cases where you have one single
pi term, right?
So the
takeaway there is that if one pi term becomes out, if k minus r is equal to 1,
you only need one experiment,
and you get a constant, and that pi term is always going to be equal to that constant.
For 2 pi terms.
Okay.
Or if k
minus r is equal to 2. Pi 1 some unknown function of pi 2. Okay.
So this leads
us to be able to write or to plot this on a two-dimensional set of axes. This leads to a curve. So
for a problem like this,
you might say
I've got
pi 2 on the x-axis,
pi 1
on the y-axis.
I'm going to go out and I'm going to collect some
experimental data.
So you would
systematically vary the value of pi 2,
measure
the dependent variable, calculate pi 1, and plot them.
Then you go through the
process of correlating this data,
which really just means in this case
fitting a curve through it.
So if you were
to fit a empirical curve through this data, okay. And say use a empirical curve fit used to represent the functional relationship between pi 1 and pi 2.
Yes, if you
go through this process, you correlate your data, and the idea is that this curve is universally applicable
to problems
governed by the same physical phenomena.
So to demonstrate
this,
I'll give you
a second to finish.
Writing.
As
an example of
this,
we're going to go back to our earlier playing around with this idea of pipe flow and pressure drop.
Okay.
Now that you guys have all gone
through
lab 3 exercise,
you understand, right?
Pressure taps,
measure the drop in pressure divided by the distance between those taps,
and you get
an approximation of pressure drop per unit length. Right.
So suppose we're given some experimental data for a pipe that is about 0.04 diameter. This is supposed to be mu. The dynamic viscosity and density of the water indicate to us that it is,
or of the fluid indicate that it's water
flowing through the pipe.
And we're given
that it's 5 foot length pipe, highest diameter diameter, different flow velocities, and someone measured pressure at each end of this 5 foot length of pipe, and gave us the pressure drop. Similarly, for one-off case, double the length of the pipe, and bump the diameter up. So maybe someone just went out and they found a weird random piece of data, and they threw it into this data set, and they gave it to us. The question is, these data here to predict pressure drop over a 2 meter length, 10 centimeter diameter, 5 meter per second flow, and same length. So it's going to bump that speed up. We'll say 3 meters per second, and double the velocity, double the diameter. Okay, so we've got a couple different. This pipe has nothing in common with this pipe that it's carrying water. It's also we're describing a totally different system of units. So how would we go through this process? This is gonna take a second. So I've transcribed those sample data into the spreadsheet here. We've got the length, we've got the diameter, the flow velocity through the pipe, and that measured pressure drop. And then I've simply taken that pressure drop and divided it. That pressure drop over here and divided it by the length over here to get the pressure drop per unit length. So we've done that in imperial units at the top, and then I've simply taken those same measurements and I've translated them to metric units down here on the bottom.
So in order to create this data correlation and actually use the correlation in new conditions,
we need to calculate our pi terms.
Okay, so first it's going to be the Reynolds number, which is the first the pi 2,
which is equal
to rho times v times d over mu.
And that's supposed to be
the mu. There we go.
So if we say this is equal to density,
okay,
slugs per feet
cubed
times the velocity times the diameter divided by the dynamic viscosity. We can calculate that for each case.
Okay. Right. No.
Don't tell me that. I'm missing a data
point here. 28.95. There we go.
There we go. All right. Now let's. There we go. So we've got
our list of Reynolds numbers.
We do the same thing
here. Taking the pressure gradient times diameter over squared. That times diameter divided by rho times v squared.
And we end up with the pressure drop coefficient. If I were to go through
this exact same process, let me
paste it in here
and change these
references to the metric
cells.
Notice that whether we're working in
imperial or metric units,
our dimensionless pi terms being the same on top of zero. Within round off error. There's a little bit of error due to the unit conversions that I did. There's one value in dimensionless terms, independent of system of unity use. And I forgot parentheses on that. There we go. Okay. So now if we plot these data on a set of axes, we're going to end up with something that looks like this. Either set of data, whether you plot it from imperial data or dimensional data, it doesn't matter, right? Because the pi terms are between the two. So if we plot these data out, we're then able to use, for example, trend line tool in Excel, or the curve fitting toolbox in MATLAB to fit a line through it. So our equation in this case is about 0.15 times x to the negative about 0.25. Okay. So this is our correlation for our experimental data. Next up, we take the conditions that we're interested in investigating. So we've got our 2 meter long pipes, 10 centimeters, 20 meters, or 20 centimeters in diameter, with velocities of 1 and 3 meters per second. What we need to do is calculate the independent pi term, look up the value on the right, and get our dependent pi term out of it, and then redimensionalize that into pressure drop. So Reynolds number can be velocity times density times diameter divided by viscosity. Okay. So then to look up the pressure coefficient, we plug in our Reynolds number into this empirical curve that we just fit. So we say this is equal to the Reynolds number raised to the negative 0.246 power times 0.1513. Do the same thing. Second case. And we can plot those on the same curve and see that they follow the work directly interpolating them from our previous experimental data. Got the green plus the Reynolds number and the red X for the first case. So that gets us this pressure drop coefficient, right? The PDL times D over rho v squared. And then because we know all the other quantities in there, we can calculate the pressure drop length per unit length. Okay, by taking this value dividing by D dividing by rho v squared, and then calculate the pressure drop over the entire length, simply multiplying that by the length pipe. And we've got now useful engineering result. Right? 180 Pascal drop to one to the other, and 530 Pascal drop to the other. For these completely new designs, or totally different types of pipes. A few things of note here. It's important to know that the correlation for the empirical curve, right? Is only valid inside the range of experimental data. And what I mean by that is if we are operating I2 Taiwan, we
go
go
out and run experiments.
This is a classic
This is a classic
case.
case.
This is what the drag
on a cylinder
looks like.
If you test it,
or the
dimensionless drag on a cylinder looks like. If you test it,
so if we fit a curve
through this,
we might be
inclined to have something that looks like this.
So if somebody asked us, okay, now what's the drag on this? Totally different design.
Calculate the wind drag on a flight outside. Reynolds number our two term might be way out here.
We don't have
enough data
to reliably predict.
Extrapolate.
So if we were
to
try using our correlation
to
predict
the
second
pi term, or the dependent pi term out there, we'd end up with that green x.
When in reality,
if we were to go out and do more experiments, what we would see is that there's this big shift
in the experimental
data.
And so only
interpolate,
never
extrapolate. That's the takeaway here.
Cases where we have 3 pi terms.
Right?
Okay. R is equal to 3.
Pi 1
to an unknown
function of
pi 2
and pi 3.
So if
one pi term gives us a constant,
2 pi terms gives us
one single curve.
3 pi terms is going to give us surface or a family of curves.
So
the way this would
typically be represented is you would go out, get your experimental data, pi 1,
your dependent
pi term of interest,
y-axis.
Let's
say we put
pi 2
on
the x-axis,
and then we create
a
series of curves
by holding pi 3
as a constant
while we vary pi 2.
So C1,
pi 3 is 2. 3.
So we end up with a family of curves. So this comes back to your question, Dylan,
about
if we had some
superfluous pi terms in there,
something
that doesn't actually affect the problem.
The idea is
now let's say we have a relationship that come up with 3 pi terms, but in reality physics are totally unimplementable.
Okay.
Then as we systematically vary value pi 3 to experiment varying pi 2, all of these curves will just fall on top of one, indicates that there's no dependence on pi 3.
So coming back to
again what you guys just did in the lab.
All right. So we've used
the flow through a smooth pipe
as an example of two pi terms. But
what's another source of variation you guys explored in the lab number 3?
Heard it
whispered.
Surface roughness.
Right? A smooth pipe and you had a rough pipe.
So the way you would draw that is,
or the way you would write that is,
you have what's
called the
you have something that's
akin to the pressure drop coefficient.
So we could say
the delta
L
times d
over rho v squared is some function of rho v d over mu Reynolds number, and then epsilon over d, where epsilon is the height of the average roughness element. Okay. The idea is this is some measure. You would use a tool called a profilometer to measure the variation in the surface elevation inside of the pipe, and come up with an average representative roughness height. So if you did this, right, you would end up with curves kind of like we did in the previous example of pressure drop coefficient versus Reynolds number, but there would be a different curve for each value of surface roughness. And that leads to something we're going to talk about a lot in the next chapter called the Moody diagram. So we've got on the x-axis, on the y-axis, they changed their dimensional analysis a little bit. Define a new term that's called factor. Really just 2 times the pressure drop coefficient that we defined. And then we have a series of curves. Each curve connects to a value of epsilon over d, which is the dimensionless height
roughness inside of the pipe.
And so if you have a measurement of how rough the pipe is, and you are able to calculate the random flow through that, the idea is as an engineer, you'd say, okay, maybe I've got a roughness, non-dimensional roughness of 0.04, and I've got a Reynolds number of 10 million. You'd move up here, find the intersection of that curve, and then move over here to the left, and say I've got a friction factor of 0.027. So that allows you to find the pressure drop. This is one of these tools that engineers doing any kind of pipe distribution design, certainly those of you that are civil and environmental engineering, can get really familiar with the Moody diagram. This is a staple of practicing engineers. Okay. So that deals with representation of experimental data for 1, 2, and 3 pi terms. If we go into more pi terms than that, if we have 4 pi terms, it is now we need to have a family of this set of axes, right? And we start to get into cases where we're not really saving ourselves effort by doing the dimensional analysis, but we still have too many variables to explore manually. Okay. So summarize this by saying for 4 or more pi terms, experiments become too expensive to make these universal correlations practical. Okay. Because again, the law of full factorial kicks in. If you have 4 variables, 4 pi terms, 5 values of each of those, then you've got 5 raised to the 4th power experiments to perform, and it increases exponentially as you add more data points for each of those variables. So in cases like that, right? What do we do? The approach there. This brings us into what we call model scaling. And the idea here is we're not going to come up with a universal relationship. We're not going to try to come up with something that we can use as a design tool. We're simply going to use this dimensional analysis as a way of analyzing a specific design. So instead of saying I want to know what the pressure drop through any kind of pipe is, we might say I want to know what the pressure drop through this specific prototype or design proposed design is. So that's something we're going to cover more in the next lecture. That's probably my favorite topic from this chapter. But the idea there, motivation or what allows us to do that is recognizing this dimensional analysis we're using to try to uncover these unknown relationships between variables. But what's to say that we can't use a known relationship and perform dimensional analysis on that? What's our most general equation that's going to govern a fluid flow? Okay, what's the one we just came up with? Where we said we're going to throw all the physics we know into this equation. Navier-Stokes. Right. So we've got Navier-Stokes and then the continuity equation. Our most generally applicable. Our are most generally
applicable governing equations.
So if we write out the Navier-Stokes equations in two dimensions,
we'll say we've got 2D. We've got rho du dt plus rho u du x plus v du dy to negative p x plus mu squared u squared plus d squared u y squared
for the x
momentum rho dv dt plus rho dx plus v dy to negative p dy.
In this case,
we'll include rho g. We'll assume
gravity's only
acting in the y direction. Mu squared v squared d squared dy squared. And continuity. dy is equal to.
Okay. So we've got these relationships. They're valid. We just don't know what the actual. So this is something that tells us that there's a well-defined relationship between different variables. So we could take this and perform a dimensional analysis on the Navier-Stokes equations and the continuity equation directly.
It's a little bit different than we've been doing because instead of repeating variables from inside here, we are going to define repeating variables based on the problem we're applying this to.
What I mean by that is if we define reference variables of we'll say v, which is going to be known as a characteristic velocity. Okay, this might be something like the speed of an object moving through a fluid, or it could be the free stream speed of a fluid flowing past a fixed object. It's simply a velocity that is important to the problem, and a well-known velocity. Okay. You can have L, which is our characteristic length. Okay. So if we're dealing with something that's like a sphere moving through a fluid, we might choose the diameter of that sphere as our characteristic length. If we're dealing with something like a boat that's moving through the water, we might choose the length of that boat. And so this is simply again some length scale that is important to the problem. And then P naught is our characteristic pressure. So we can pick something like atmospheric pressure. If we think that's the problem, or vapor pressure. If we think we're going to be dealing with really low pressures and habitation. And if we use these as our repeating variables, we can non-dimensionalize both momentum equations and the continuity equation using these variables. And I'm going to skip over all of the math here because it doesn't really do much for us until we get to the very end. If you want to see the math, it's the section 710. The idea is what comes out is a dimensionless version of continuity and Navier-Stokes.
with
some
classic
high terms
as coefficients.
And so those pi terms basically we're dividing things through. We've got let's take a look at the viscosity momentum
equation.
We've got
viscosity here.
Is if we
divide that
by V and L, and if we divide everything else in here by for example, we end up with a Reynolds number there. And so it's a classic pi term that's included as a coefficient on some of our other variables. But these
variables have special meaning, and they're really common in fluids, and so we could do a quick run through what they actually are.
So that's it for
non-dimensionalization Navier-Stokes. The idea is I wanted to explain what we use to non-dimensionalize it. The idea is we non-dimensionalize it, and what we get is sort of a list of these important
pi terms. So the first one is I mentioned this before, the Reynolds number. Essentially what this represents is a ratio of the relative importance of inertial forces to viscous forces. So we've got those different forces in our Navier-Stokes equations, right? The inertial forces would be the density times our acceleration, right? And the viscous forces would be everything that is prefaced by that viscosity. So somehow by non-dimensionalizing Navier-Stokes, we end up dividing one of those by the other. What comes out as the Reynolds number. Rho v times our characteristic length over mu. So because it's inertial over viscous force, the idea is really low Reynolds numbers. This means that viscous forces dominate. This is common in things like creeping flows, or flows where it tends to out very quickly. So stirring paint, etc. At higher Reynolds numbers, inertia tends to become important. So you can see here, for example, rotating an object has a floating, rotating a cylinder of liquid that has an object in it. If you bring it to a stop, low Reynolds number, the object stopped almost immediately because the viscous drag brought its velocity to zero. The larger Reynolds number continued on because its own inertia started to become comparable to the viscous stresses on it. The Froude number, we're not going to be able to finish all of these, so we'll pick these up again in the next lecture. The Froude number is defined as V over square root of GL. This is the ratio of inertial forces to gravitational forces. This is really important in a lot of things like flow in rivers, flow over dams, flows around boats, or inside of tanks, because the fact that we're balancing inertial and gravitational force means that this dictates the behavior of things like waves. So there's a nice example I'll do in the beginning of the next lecture that demonstrates how we can use the Froude number to show why, for example, tsunami waves travel faster than ripples in a pond. Euler number is the ratio of pressure-based forces to inertial forces defined by P, our reference pressure in this case, over rho v squared. This is important to things where, or this is important in cases where we may have, for example, cavitation. The cavitation number is a Euler number. It's also used to represent dimensionless pressures for things like aerospace structures, right? They used to then calculate lift. The Mach number. This one doesn't actually come from the Navier-Stokes equations, but we added in because it's important for cases where we have compressible flow. This represents the ratio of inertial forces to forces resulting from compressibility, springiness of a fluid. It's the ratio of characteristic velocity to the acoustic speed or the speed of
sound in the fluid that
we're
we're considering.
So
generally, if the Mach number is below 0.3,
this means
that
compressibility forces are much greater than inertial forces. Meaning that the fluid is going to act very stiff. It's going to behave as if it's
incompressible.
For Mach numbers
greater than 0.3, inertia is going to tend to
actually
compress the fluid. It's going to behave like a looser
sort of bulk spring.
So compressibility effects become important.
And the Struhel number
is probably my favorite. If you're my favorite dimensionless number.
Struhel number is a good one to
have.
This is
the ratio of unsteady inertial forces. So the local acceleration term in your Navier-Stokes equations
to the steady
inertial forces,
which is
the convective acceleration term. This is defined as omega, which is a characteristic frequency times a length over velocity.
And so this is
something we see a lot when we're describing called vortex shedding, singing wires, or the flow past cylinders.
So here we've got
smoke visualization past a very small cylinder in a wind tunnel.
And we see we get these
alternating vortices.
Similarly,
we've got satellite imagery
cloud formations
behind islands. Show exactly the same pattern. The idea here is that you can see that there's a really regular spacing these vortices.
And that's because
this shedding occurs at a constant Struhel number.
So this is one of those
cases where we can say
the
shedding behavior is governed by one single pi term.
Struhel number
equals constant.
And it applies
whether you're in a wind tunnel this large
or whether you're in the Pacific Ocean
over the scale of miles.
All right, we will pick this back up
on credit.